Have you ever felt a presence you couldn't see? A subtle pull, an unseen force shaping the world around you? Out in the cold, dark frontiers of our own solar system, something is hiding. For years, astronomers have been gathering clues, piecing together a puzzle that points to a startling conclusion. We may not know our cosmic neighborhood as well as we thought. Scientists, I believe, are standing on the precipice of a discovery so profound it will force us to redraw the map of our own celestial backyard. The evidence is mounting, whispering of a ghost in the machine, a massive, unseen world lurking far beyond Neptune. This isn't just a story about finding another rock floating in space. This is about Planet 9, a hypothetical giant that, if it exists, could fundamentally rewrite our understanding of how our solar system formed and evolved. Its discovery would be a testament to human curiosity, to our relentless drive to peer into the darkness and find what's there. It would answer questions we've been asking for decades and raise entirely new ones. The search for Planet 9 is more than an astronomical hunt. It's a quest to complete the census of our own home, to find a missing member of our cosmic family. So, join me on a journey to the edge of the known, a place where gravity tells a story, and the orbits of tiny frozen worlds betray a giant secret. We'll explore the tantalizing evidence, the cutting-edge technology, and the brilliant minds dedicated to this epic search. We'll weigh the theories, confront the challenges, and consider what it would mean to finally, definitively, welcome a new planet into our solar system. The cosmos is calling, and it's telling us there's something more to find. Let's go look for it together. Our story begins not with a telescope, but with a spreadsheet. It begins with numbers, with the strange and unlikely choreography of a handful of tiny worlds dancing in the dark. Far beyond the orbit of Neptune lies the Kuiper Belt, a vast, icy debris field left over from the formation of the solar system. It's populated by countless frozen bodies, often called trans-Neptunian objects or TNOs. For the most part, their orbits are what you'd expect, scattered, random, a mess of cosmic leftovers. But a few of them, a special few, are doing something odd. Imagine standing in a field during a light breeze, and you see 6 leaves on the ground all pointing in the exact same direction, tilted at the same angle against the Earth. You'd rightly suspect it wasn't a coincidence. You'd look for a cause, perhaps a hidden sprinkler head pushing them all into alignment. Astronomers looking at a small group of the most distant TNOs found the cosmic equivalent of this. These objects, against all statistical odds, have orbits that are clustered together. They all swing out into space in the same general direction. This isn't just a directional alignment. Their orbits are also tilted, similarly, relative to the flat plane where all the major planets orbit the Sun. It's as if an unseen hand has reached out into the void and organized these distant wanderers. The chance of this happening randomly is minuscule, something like 1 in 14,000. When scientists see something that improbable, they don't chalk it up to luck. They look for a reason. They look for the source of the gravity that must be shepherding these tiny worlds. The gravitational pull of the known planets, Jupiter, Saturn, Uranus, Neptune, isn't strong enough to have this effect at such vast distances. Their influence wanes, becoming too feeble to corral these distant objects. So, the data screams out for another explanation. Something else must be out there. Something big. Something with enough gravitational muscle to herd these icy bodies into their strange, synchronized dance across billions of miles of empty space. This clustering is the primary breadcrumb, the gravitational fingerprint of a phantom. It's a clue written in the language of physics, pointing toward the existence of a massive, unseen perturber. This is the genesis of the Planet 9 hypothesis. Not a direct sighting, but a deduction. A conclusion born from the subtle, yet persistent alignment of the solar system's most remote inhabitants, telling us that they are not alone. The whispers of a hidden planet have echoed through astronomy for over a century. Percival Lowell famously, and incorrectly, searched for a planet X to explain supposed wobbles in the orbits of Uranus and Neptune. That search led to the discovery of Pluto in 1930. But Pluto was far too small to be the giant Lowell envisioned. The modern hunt for Planet 9, however, is a different beast entirely. It's not based on flawed calculations of the inner giants, but on the compelling evidence from the solar system's outer fringe. The starting gun for the modern search was fired in 2016. That's when astronomers Konstantin Batygin and Mike Brown at Caltech published their groundbreaking paper, They didn't just point out the weird clustering of the TNOs, they did the math. They ran complex computer simulations to figure out what could be causing it. They tried everything, a fluke, a swarm of smaller objects, errors in the data. But the simulation that perfectly reproduced the observed orbits time and time again was one that included a new, ninth planet. Their paper wasn't a claim of discovery, but a roadmap. It was a treasure map, in a sense. It said, based on the gravitational effects we see, there should be a planet of about 5 to 10 times the mass of Earth, on a vast, elongated orbit, and it should be somewhere in this general area of the sky. This announcement electrified the astronomical community. It transformed the idea of a hidden planet from a fringe fantasy into a respectable, data-driven hypothesis. Immediately, telescopes around the world were retasked. Astronomers began poring over archival data, looking for anything they might have missed, a faint dot moving slowly against the background of stars. Observatories with wide-field survey capabilities, designed to map huge swaths of the night sky, became the frontline soldiers in this new war on cosmic ignorance. The search was no longer a passive observation, it was an active hunt. Mike Brown, ironically one of the key scientists responsible for Pluto's reclassification to a dwarf planet, now found himself leading the charge to find a true new planet. He and Badigan, along with teams across the globe, began a systematic and painstaking search of the regions of sky their models predicted. The race was on. The search wasn't just about finding a planet, it was about validating a powerful new method of discovery, inferring existence through gravity's subtle touch. So how do you find a planet that might be 1,000 times farther from the Sun than Earth, and 100,000 times fainter than Neptune? You can't just point a backyard telescope at the sky and hope for the best. This hunt requires some of the most powerful and sophisticated astronomical instruments ever built. The primary tool in this quest is the Survey Telescope, a special kind of observatory designed for breadth, not just depth. Think of it like this: a telescope like the Hubble is a sniper rifle, designed to look very closely at one tiny, specific spot. A survey telescope, on the other hand, is a wide-angle camera with a massive field of view. Its job is to repeatedly photograph huge patches of the night sky. The key is the repeatedly part. A planet, even one as distant and slow as Planet 9 is thought to be, will move. Against the fixed backdrop of distant stars and galaxies, it will crawl across the heavens from one night to the next. The Subaru telescope, perched atop Mauna Kea in Hawaii, has been a major player. Equipped with the Hyper Supreme Cam, an 870-megapixel digital camera, it can capture an area of the sky 9 times the size of the full moon in a single shot. By taking images of the same region days or weeks apart, astronomers can use software to compare them, looking for that one faint dot that has shifted its position. This is the digital equivalent of a cosmic spot, the difference game. Another workhorse has been the Dark Energy Survey, or DES. While its main goal was to study the expansion of the universe, its vast archive of images of the southern sky is a treasure trove for planet hunters. Scientists have been meticulously combing through this data, a process known as data mining, looking for the telltale signature of a slow-moving object that fits the profile of Planet 9. It's a needle-in-a-haystack problem of astronomical proportions, and the future of the search is even more exciting. The Vera C. Rubin Observatory, currently under construction in Chile, is set to revolutionize this field. When it comes online, it will survey the entire visible southern sky every few nights with its 3,200-megapixel camera. Its sheer data-gathering power is unprecedented. If Planet 9 is out there and it's within the brightness range we expect, the Rubin Observatory stands the best chance of any instrument in history to finally pin it down. This is technology pushing the boundaries of the possible. While we haven't actually seen Planet 9, its gravitational shadow lets us, sketch a portrait of this hidden giant. Based on the amount of gravity needed to shepherd those far-off trans-Neptunian objects, scientists have been able to estimate its fundamental properties. The leading models suggest that Planet 9 has a mass of about 5 to 10 times that of our own Earth. This puts it in a really fascinating category of planet, a so-called super-Earth, or a mini-Neptune. This mass, honestly, is significant. It's much too large to be a rocky planet like Earth or Mars. At that size, its gravity would have been strong enough to hold onto a thick, primordial atmosphere of hydrogen and helium gas, left over from the solar system's formation. So we're probably not looking for another Earth out there. Instead, we're likely hunting for a smaller version of our own ice giants, Uranus and Neptune. It would be a cold, gaseous world, with a solid core wrapped in a deep mantle of exotic ices and a thick, crushing atmosphere. Its orbit is, perhaps, its most dramatic feature. The models predict a highly eccentric or elongated path around the Sun. At its closest point, perihelion, it might be around 200 to 300 times farther from the Sun than Earth is. But at its farthest point, its aphelion, it could swing out to a staggering 600 to 1200 times the Earth-Sun distance. This vast orbit means its year, the time it takes to circle the Sun once, would be immense, somewhere between 10,000 and 20,000 Earth years. Because of this enormous distant orbit, Planet 9 would be incredibly cold. With the Sun appearing as little more than an unusually bright star in its sky, surface temperatures would plummet to around minus 225 degrees Celsius, or about 400 degrees Fahrenheit, below zero. It would be a world of perpetual twilight, shrouded in darkness and frozen to its core. There would be no liquid water, no familiar landscapes, just a silent, colossal ball of ice and gas, wandering the lonely outer darkness. The question of its origin is also, honestly, pretty compelling. Was it formed out there in the cold, slowly gathering material in the early solar system? Or, as some theories suggest, did it form closer to the Sun, maybe near Jupiter and Saturn, and then get violently ejected into this distant orbit by a gravitational tussle with those giants? Finding it won't just tell us what it is, it could also tell us about the chaotic and violent adolescence of our own solar system. If Planet 9 is as massive as 10 Earths, you might wonder, why haven't we found it yet? The answer lies in a pretty brutal combination of three factors: distance, darkness, and size. The size of the sky, that is. The sheer scale of the challenge is, honestly, tough to wrap your head around. Planet 9 is thought to be on an orbit that takes it hundreds of times farther from the Sun than we are, and the brightness of an object falls off with the fourth power of its distance. Let me break that down. If you move an object twice as far away, it doesn't just look half as bright, or a quarter as bright. Because it's reflecting sunlight, the light has to travel from the Sun, and then from the planet. So if the planet is 10 times farther away, the sunlight reaching it is 100 times dimmer, and the light returning to us is dimmed by another factor of 100. It ends up being 10,000 times fainter. At the predicted distances for Planet 9, we're talking about an object that is millions of times fainter than Neptune. The second problem is that we don't know exactly where in its vast orbit the planet currently is. The models give us a path, a kind of celestial highway it travels on, but they don't give us its precise location on that highway. It's currently thought to be near its aphelion, its farthest point from the Sun, which makes it as dim and as slow-moving as it can possibly be. This makes it exceptionally difficult to distinguish from the faint, distant stars that fill the background. Then there's the sheer size of the search area. The predicted path of Planet 9 traces a huge swath across the celestial sphere, and because of orbital uncertainties, that path is more of a wide, blurry band than a sharp line. Searching this entire region with the precision needed to spot such a faint object is like, well, trying to find a single, dark-colored marble somewhere on the continent of North America using only satellite photos. It's an immense volume of space to survey. Finally, the very thing we're looking for, its slow movement, is also a challenge. To confirm an object is in our solar system, you need to see it move relative to the background stars. But at its extreme distance, Planet 9's apparent motion is glacial. It would take weeks or even months of observation to confirm its leisurely crawl across the sky. All these factors combine to make this one of the most difficult astronomical searches ever undertaken. The hunt for Planet 9 is a dynamic and evolving story. It's not just a single search, but really a global effort, and every new piece of data can refine the map and bring the treasure closer. In recent years, the search has intensified, and while the planet itself remains elusive, Soginen, Sominerber Dean, Sunninatsen Silver, Soinen, circumstantial evidence has just continued to grow. Astronomers are finding more and more of these strange trans-Neptunian objects, and they continue to fit the pattern. One of the most significant recent developments has been the discovery of additional TNOs that show the same bizarre clustering. The original hypothesis was based on just a handful of objects. As surveys like the Dark Energy Survey and others have discovered more, the statistical significance has held up. It's kind of like finding more leaves on the ground, all still pointing in that same unlikely direction. This really strengthens the case that a single, massive perturber, Planet 9, is the most elegant explanation. Furthermore, the models themselves have been refined. By incorporating the orbits of these newly discovered TNOs, Badigian, Brown, and other teams have been able to narrow down the probable characteristics of Planet 9. The latest simulations have slightly revised the estimated mass down to about 5 Earth masses, and have provided a more constrained search area in the sky. The treasure map is becoming less of a sketch and more of a detailed chart. There have also been tantalizing, though unconfirmed, candidates. Periodically, an astronomer will spot a faint object moving in a way that could be consistent with Planet 9. These moments cause a flurry of excitement in the community. However, follow-up observations are required to confirm the orbit, and so far, each of these candidates has either been ruled out, maybe it was an object on a different orbit, or even just instrumental noise, or has been lost before its path could be confirmed. These near misses are not failures, they're actually a crucial part of the scientific process. They show that the technology is sensitive enough to potentially spot the planet. They help astronomers refine their search techniques and rule out sections of the sky. Each new TNO discovered, each improved simulation, each candidate that is investigated and ruled out, is a step forward. We are not wandering in the dark, we are systematically illuminating it, one patch of sky at a time. A good scientific hypothesis must be testable, and, it really has to be better than the alternatives. While the Planet 9 hypothesis is, honestly, pretty compelling, it's not the only explanation out there for the strange orbits we see in the outer solar system. Science demands skepticism, so it's crucial we examine the other possibilities. What else could be shepherding these icy worlds? Well, one alternative theory suggests that it's not a single large planet, but actually the combined gravitational influence of many smaller objects. Maybe the Kuiper belt is more massive than we currently think. If there were enough dwarf planets and smaller bodies out there, their collective gravity, over billions of years, could potentially nudge the trans-Neptunian objects into the observed alignment. It's kind of a gravity by committee model, rather than the gravity by a single CEO model of Planet 9. The challenge for this theory is that honestly, we haven't yet observed nearly enough mass in the Kuiper belt to make the numbers work. Another idea is that the clustering is just a statistical fluke. While the odds are low, they aren't zero. It's possible that we have, just by chance, happened to discover a handful of TNOs that look aligned. This is known as an observational bias. Maybe our telescopes are just more likely to find objects in that particular region of the sky, or with those particular orbital characteristics. As we discover more and more of these objects, this theory becomes less and less likely, but it can't be completely dismissed until the sample size is much larger. A more exotic theory, and this one's really out there, posits that the gravitational pull isn't from a planet at all, but from something far stranger, a primordial black hole. This wouldn't be a black hole formed from a collapsed star, but a microscopic one, maybe the size of a grapefruit but with the mass of 5 Earths, actually forged in the Big Bang itself. Such an object would be completely dark and impossible to see directly. It would only be detectable by its gravity, which is, well, exactly the evidence we have. This is a fascinating, though highly speculative possibility. Finally, some have proposed that our understanding of gravity itself might be just a bit off. Modified Newtonian dynamics, or MOND, is a fringe theory that suggests gravity behaves differently on galactic scales. While it's primarily aimed at explaining galaxy rotation without dark matter, some have tried to apply its principles to the solar system. However, these models have struggled to reproduce the specific clustering we see. For now, the Planet 9 hypothesis, a single, unseen planet, remains the simplest and most elegant explanation that fits the data we have. The discovery of Planet 9 would be a monumental moment in the history of science, a headline that would resonate around the globe. It would be the first time a new planet has been added to our solar system's roster in nearly 170 years, since the discovery of Neptune in 1846, which, incidentally, was also found through its gravitational influence before it was seen. It would be a profound confirmation of the power of prediction in science. On a fundamental level, it would change our picture of home. Our solar system, which we thought we had neatly catalogued, would suddenly have a new major component. The neat division of 4 rocky inner planets and 4 outer gas and ice giants would be upended. Planet 9, a super-Earth or mini-Neptune, would represent a class of planet that is incredibly common in other star systems but conspicuously absent from our own. Finding one here would fill that gap in our planetary census. Its existence would provide a crucial key to unlocking the secrets of our solar system's early history. How did it get there? If it was ejected from the inner solar system, its orbit is a fossil record of the chaotic gravitational dance of the giant planets in their youth. Studying its composition and path would allow us to test and refine our models of planetary formation and migration, giving us a clearer picture of the violent processes that shape the very architecture of our cosmic neighborhood. Beyond the science, the discovery would have a deep cultural and philosophical impact. It would be a powerful reminder that our knowledge is incomplete, that there are still great discoveries to be made right here in our own backyard. It would ignite the public imagination, inspiring a new generation of scientists, engineers, and explorers. The very idea of a new, massive world in our solar system, a planet 9, stretches our sense of place and possibility. It forces us to look up at the night sky with fresh eyes, to wonder what else might be hiding in the dark. It underscores a fundamental truth about the universe. It is vast, mysterious, and always has more secrets to reveal to those who are patient and clever enough to look. The confirmation of Planet 9 would not be an end to a story, but the beginning of a whole new chapter in our exploration of the cosmos. The hunt for Planet 9 is accelerating. We are entering an era of unprecedented survey power, and the next decade promises to be the most exciting yet in this cosmic detective story. The key to the future of the search lies in a new generation of observatories and a smarter way of analyzing the mountains of data they will produce. The primary instrument that has astronomers holding their breath is the Vera C. Rubin Observatory. Currently nearing completion on a mountaintop in Chile, the Rubin Observatory is a machine built for discovery. Its mission, the legacy survey of space and time, will scan the entire southern sky every few nights for 10 years. The sheer volume of data it will collect is staggering, about 20 terabytes every single night. That's like streaming high-definition movies continuously for over 2 years every single night. Within this deluge of data, the slow-moving signature of Planet 9 should, if it's there, stand up or stand out. The LSST will create the deepest, widest movie of the universe ever made. Its sensitivity and rapid cadence are perfectly suited to finding faint moving objects in the outer solar system. The team led by Betagen and Brown has already secured observation time and is developing sophisticated algorithms to automatically sift through the LSST data stream, flagging potential candidates for Planet 9 in near real time. This moves the search from a painstaking manual process to a highly automated one. But ground-based telescopes aren't the only hope. Existing space telescopes like Hubble and the James Webb Space Telescope could be called upon for follow-up observations. Once a strong candidate is identified by a survey telescope like Rubin, a more powerful telescope could be pointed at it to confirm its nature and even attempt to study its color or composition, giving us our first real clues about what this distant world is made of. So the strategy is clear: use the wide-eyed survey telescopes to find the needle in the haystack, and then use the sharp-eyed precision telescopes to examine that needle up close. The next few years will be a period of intense anticipation. As the Rubin Observatory begins its decade-long survey, every new image could be the one. The data is coming, the tools are ready, and the scientific community is poised to analyze it. The final act of this discovery may be just around the corner. This grand cosmic search is a story that is unfolding in real time, and you are living through it. The discovery of Planet 9, if and when it happens, will be a moment shared by all of humanity. It's a journey of discovery that belongs to everyone who has ever looked up at the stars and wondered. Staying connected to this ongoing quest is easier now than ever before, and it allows you to be part of the excitement as it happens. The search for Planet 9 is a perfect example of the scientific process in action. A hypothesis is formed from evidence, predictions are made, and technology is built to test those predictions. It's a story of persistence, ingenuity, and our unyielding desire to understand the universe. Every new paper published, every new trans-Neptunian object catalogued, every new survey that comes online is another scene in this unfolding drama. It's a narrative I'm deeply passionate about sharing. Here, we're dedicated to following this story every step of the way. We'll break down the latest findings from the Rubin Observatory, explain the significance of new computer models, and bring you interviews with the very scientists on the front lines of the search. Our goal is to be your portal to the outer solar system, translating the complex data and dense scientific papers into a clear, compelling narrative that we can all explore together. By being a part of this community, you ensure you won't miss the moment the news breaks. When that faint dot of light is finally confirmed, when the map of our solar system is officially redrawn, you'll be among the first to understand not just what was found, but why it matters so much. The universe is constantly revealing its secrets, and this channel is your front row seat. So, if you're as fascinated by this cosmic mystery as I am, if you want to follow the clues as they are uncovered, and be there for the potential climax of one of the greatest astronomical hunts in modern history, then I invite you to join us. The journey is far from over, and the most exciting chapters may be yet to come. Let's stay curious and keep exploring together. We stand at a remarkable moment. The evidence points to a hidden giant in our solar system, a Planet 9 waiting to be found. We've journeyed through the evidence written in gravity, explored the incredible technology driving the search, and contemplated what it would mean to find a new, massive member of our planetary family. The story is far from over. In the coming years, as new observatories like the Vera C. Rubin begin their work, we may finally get an answer. The darkness at the edge of our solar system holds a secret, and we are closer than ever to revealing it. This quest is a testament to the human spirit. It's a story about looking at a few strange data points and daring to imagine a whole new world. Whether we find Planet 9, or a primordial black hole, or discover that our understanding of gravity needs a rewrite, the result will be a profound leap in our cosmic awareness. The search itself enriches us, pushing the boundaries of technology and theory. It reminds us that there are still vast, unexplored frontiers, even in our own backyard. The universe is under no obligation to make sense to us, but it is our greatest privilege to try and understand it. As this incredible story continues to unfold, we'll be here to track every development and share the wonder of discovery with you. The cosmos is full of mysteries, and the search for Planet 9 is just one of many adventures. If you want to continue this journey with us, to be there for the next big revelation from the depths of space, make sure you're subscribed. The greatest discoveries are yet to come.